Okay, you guys, I'm going to do another recording. This is another intro. I'm going to show you an example of trig substitution. That's the gist of this, so you get a feel for it. Trig substitution is a clever and challenging method of changing an integral into something you can integrate. And then oftentimes you have to go back to your original variable. It's really a good method for these types of problems where you've got like a squared minus x squared, etc. And we're relying on the identities that say, well, for instance, maybe you remember that, I hope you do, sine squared theta plus cosine squared theta is what? It's equal to 1, right? So if I could write it. But there's another one. Tangent squared theta plus 1 is secant squared theta. So these guys are helpful to us in these problems. I'll give you, for instance, here's the motivation right here. Suppose we were able to, and maybe some math guy or gal dreamt this up one day on a rainy day, unlike today. And what if I could replace x squared with 9 sine squared? Wouldn't it be nice? I sometimes sing that song by the Beach Boys. Wouldn't it be nice? Wouldn't it be nice if you could do that? Then what happens is, look, you can factor out 9. Look, 1 minus sine squared, if you look up here and use your imagination, is cosine squared. And so now I have the square root of 9 cosine squared, and you square root it, you get 3 cosine, and you've lost the radical, and things are good. Now, on this tape, with a lot of moves going on, pause anytime you want to go, what? And stare at it a bit, and that might be a good first place to stop. Okay? What I want to do with you guys is do an example of this, and the example is this particular problem, okay? And so how can we do it? Well, on exams of the past, sometimes students will go, yeah, I don't know about no trig substitution, but what I'm going to do is I'm going to use this substitution, and I did it on paper, and I go, it works right fine. In fact, it's easier than trig substitution. You just have to be really good at U substitution. But some problems we see won't fly. You have to use trig substitution. So later when we, in this chapter, we'll talk about a table of integrals, which is through the ages, people have added integral formulas for certain types of problems. And some of those guys came from trig substitution. Wouldn't have it otherwise. So anyway, let's do this, guys. So without further ado, we're going to integrate this. I have to warn you, it's kind of a long problem, so the video is going to be kind of long too. So I'll try to go fast. What I notice is it's of the variety way up there of a squared plus x squared. So I should use a variant of tangent. Now, I haven't told you why, but you're going to see why, okay? So we're going to switch colors here and do a substitution. So what we'll do is, since I see this 4 here and I see the plus, I'm going to replace x squared with 4 tangent squared theta. Okay, that's going to take care of, now if you're good at substitution, that's wonderful. Okay, because then what happens is, well, now I know what x squared is going to be. It's going to be 4 tangent squared. Okay, but we also have x cubed here. So we have to figure out what x cubed is in terms of theta. We're going to substitute anything with an x, and that includes the dx as well. So we're going to have to do a major surgery on this problem. So first we'll say, you know what, x is, I square root both sides, 2 tan theta. Are you good with that? So if I need an x cubed, I just cube that, and I get 2 cubed is 8, tan cubed is tan cubed, like so. So now we know what goes in for x cubed. Okay, in fact, you can start writing it out. But before I do that, I'll go one more thing. This is the part that students tend to forget about. They fly by. They don't respect the dx. You should, because if x equals 2 tangent theta, if we derive that guy to find d theta or dx, we get dx is equal to 2 times the derivative of tangent, secant squared theta, and let's be thorough, times d theta. Now we know what everything is in terms of this substitution. So our problem changes. it becomes integral of x cubed. I'm going to replace it with 8 times tangent cubed of theta. Square root x squared, I'm going to replace it with 4 tangent squared theta plus 4. And then dx, I'm going to replace it with 2 secant squared theta d theta. Isn't that fun? Yeah, it's way better. Is it really? I went from here to here. It looks terrible. But because of Pythagoras, it simplifies, and we lose the square root. The square root in an integral is painful. It's painful. Okay, so let's do that. Let's get rid of the square root, and I'll show the steps. Anytime you want, just pause it. Maybe try to anticipate that I'm going to factor out the 4. Why would you do that, Weber? Well, the whole thing is set up that way for us. Okay. Inside the radical, what do we get? Well, tangent squared plus 1, remember, is secant squared. Okay, and what happens to the square root? It square roots, doesn't it? This is the beauty of the whole problem. The beauty of this technique is now we get 2 secant theta. This really is better now, because before we had a radical with x's. Now, because of Pythagoras and trig and our clever intuition, we don't have a radical. So I like to take the numbers and move them out of the way. So 8 times 2 times 2, I think is 32. And I've got a tangent cubed. And you know what else? Secant cubed. That should ring a bell. We did something similar to that in the previous video that we did. Whoops. Lost my mind. Okay. So what we do with that is a newfangled way of doing things. I'm going to split off a tangent, leaving a square, and a secant, leaving a square, so that we have secant times tangent, like we've seen before. But now, time for another substitution. In fact, I'll change the color on this substitution, okay? We're going to let u equal secant theta, because then du is the secant theta times the tangent theta d theta. The only trouble is tangent squared isn't a secant. But yes, it is if you want it to, because of trig and Pythagoras. What is it really if we want it to? It's secant squared theta minus 1. Say what? Pause, look it up, or just scroll up here and look at that equation right there. Yeah, throw the 1 over, and secant squared minus 1 is tangent squared, where tangent squared is equal to secant squared minus 1. So that is beautiful, because here comes our next, yeah, that's a second substitution. It's 32 integral. What else do we have? We've got secant squared theta minus 1. And then the secant squared is secant squared. And now I didn't do the substitute. I'm rewriting, sorry. So secant theta, tan theta. Well, that's okay. It's thorough. So now we can go, it's 32 integral. And now we have u squared minus 1 times u squared du. That's a happy integral. We're finally getting to an integrand that we can handle. 32. Oh boy, it's late in the day, folks. Can you tell? So we've got 32 integral u to the 4th minus u squared du. Hip, hip, hooray. Now, integrate. We get 32. And upon integrating, we have 1/5 u to the 5th minus 1/3 u to the 3 plus c. Also known as, what was u? Secant. So 32 1/5 secant to the 5th minus 1/3 secant to the 3rd plus c. Everything's going swimmingly. Now, we went from u Well, we went from x to theta to u. Now we went from u back up to theta. Guess what? We got to go up to x. There's different ways of doing it. This one, since it's just secant, I'll just do something weird like in a different color, maybe this color, and go, well, we know that from way above, we know this substitution. You go back to that substitution. It says, I'm sorry, making me seasick. X is equal to 2 tan theta. That means that tan theta is x over 2. But we also know that secant, because I need secant, don't I? We know that secant squared theta is equal to tan theta, tan squared theta plus 1. So our secant squared is equal to x over 2 squared plus 1. So we're getting secant squared theta, I know, tedious, is x to the 4, sorry, x squared, over 4 plus 1. But you know what? I'm going to call it x squared plus 4 all over 4, common denominator, okay? So that means that secant theta by its lonesome is the square root of x squared plus 4 over 2, okay? Plug those in and you get your final answer. So let's do that. I know, you can hear, I'm tired too. We have, I'll write it this way, 32 over 5. And then in here, we've got this square root of x squared plus 4 all over 4 to the 5th power, okay? Oh, all over 2, sorry. And then we have, what else? Minus 1/3, eyes are glazing. We've got the square root of x squared plus 4 all over 2, this time to the 3rd. And if you clean this up, you get the same answer that's upstairs. I didn't point that out to you, but the answer looks something like this. So that's 2 to the 5th. That's 32. You get 1/5, and then you get x squared plus 4 to the 5th, I think. No, 5 halves, right? And then minus, and the numbers work out to be, oh, there's a 32 here too. I forgot him. Distribute that guy. So he's 8, so he's 4/3. And then x squared plus 4 to the 3/2 power plus c. Feel pretty good about that answer. I know that maybe you turned off the video, but that's the final complete answer. If you scroll up here, you're going to find the identical answer right there. Okay, I didn't show that one, but I did the trig substitution method on it. And folks, that's all she wrote on that one. Woo, that's a toughie. I'll see you in class. Stop it.